So if you could dive into the deep ocean today, you might run into something called a ratfish.
Hmm.
And it's a creature that, well, it honestly looks like it was stitched together from spare parts.
Right.
It's got these huge eyes, a long sort of whip-like tail, and these big wing-like fins. But the weirdest part is its mouth. Its teeth are fused into these plates, almost like a beak, for crushing shells.
Mm-hmm.
Now, this strange survivor, it's called a chimera scientifically, is all cartilage, just like sharks and rays. And it's basically a living ghost, a reminder of a time we call the golden age of sharks.
A very strange leftover for sure.
And you should forget everything you think you know about sharks, like the great white. This golden age, during the Carboniferous period, was ruled by cartilaginous fish that were just astonishingly bizarre.
Truly alien-looking things.
We're talking about creatures with buzzsaws for jaws, fins that let them basically fly through the water, and maybe most famously, sharks that had an anvil covered in tiny teeth growing right out of their heads.
The anvil is it's a classic.
So, our mission for you today is pretty simple. We're going to dive into the fossil record, which is, fragmented to answer two big questions. First, what on earth happened to let them explode into all these weird specialized forms?
And second, maybe more importantly, why did they lose almost all of that spectacular weirdness forever?
Exactly.
And we should say right at the start, it's a huge challenge because we're talking about cartilage. Their skeletons they don't preserve well. It's soft tissue.
Right? Not like bone.
Not at all. So we're building this entire history from the parts that are tough. We're talking teeth, spines, and scales. They're all made of dentine, which is incredibly durable. So they left us clues, but they're more like scattered tools than complete blueprint.
Okay, so let's set the stage. Before this golden age, these early sharks weren't exactly ruling the seas.
No, not even close.
The very first hints we get are these tiny little scales from way back in the late Ordovician, maybe 465 million years ago. The first real fossils show up a bit later in the Silurian, but for a long, long time, they were just small, generalist fish, just kind of getting by.
And they were being held back. There was this enormous, heavily armored roadblock in their way, the placoderms.
That's the armored fish.
The armored fish. By the time we get to the Devonian period, say 419 million years ago, placoderms were everywhere. They were the dominant group, period. You had apex predators like the massive Dunkleosteus.
Terrifying.
Oh, just a monster. A fish that could grow up to 10 meters long with this thick armor plating and these huge shearing jawbones.
So they weren't just big, they were diverse.
They filled every single niche, deep oceans, freshwater rivers, you name it. And the general theory among paleontologists is that this complete domination kept the early sharks as, small-time players. They were stuck on the margins, they just couldn't compete.
So if the placoderms were this giant brick wall, what was the wrecking ball that finally smashed it down for the sharks?
That would be the late Devonian mass extinction. And it wasn't one single event, which is interesting. It was this prolonged crisis that started around 373 million years ago. It just stretched on for millions of years.
And what was causing it?
We think it was linked to big swings in sea level and these massive anoxic zones areas with no oxygen forming in the oceans. It was a global catastrophe. It wiped out a huge percentage of all marine life.
But not all life suffered equally. This is the turning point.
That's the pivot, exactly. The placoderms, whose whole deal was their heavy armor and their reliance on certain habitats, they just vanished completely. Gone. They were maybe too slow, too specialized, or just couldn't handle the changing chemistry of the shallow seas where so many of them lived. But the sharks made it through.
So what was their secret?
Flexibility. I mean, that's the key. They weren't tied to the seafloor. They could explore different foods, and crucially, they could venture out into the open ocean. And open ocean ecosystems tend to get hit a little less hard in these events compared to, say, shallow coastal reefs.
So their ability to move and adapt was their saving grace.
It was everything. When the dust finally settled, sharks didn't just survive the extinction. They basically inherited the entire aquatic world. Their populations just boomed in those last few million years of the Devonian.
And that boom launches us right into the Carboniferous period, 359 million years ago. And suddenly, evolution has this giant empty canvas to work with.
It's an evolutionary free-for-all. You have these warm, stable, shallow seas covering huge parts of the continents, just perfect conditions for an explosion of life and specialization.
And we're not just talking about a few new species.
No, this is why we call it the Golden Age. The scale of their domination is just staggering. In some of these carboniferous environments, especially near the shore, sharks and their relatives made up something like 60, even 70% of all the species.
70%. That's unbelievable.
They were the undisputed rulers of the water.
And we get this incredibly clear window into their world.
Oh, Bear Gulch is priceless. Just a paleontological treasure. Because the conditions there were so perfect, this calm, oxygen-free mud, it didn't just preserve teeth, it preserved complete skeletons.
Which is almost unheard of for these fish.
It's the holy grail. So this site gives us these fully formed portraits of that wild cast of characters you mentioned, creatures that were so highly specialized they would look absolutely alien to us.
Okay, let's get into some of them, because this is the really fun part.
Yeah.
You have a shark like Thrinacotis.
Right. Its body evolved to be really long and eel-like. It was clearly designed to snake through tight spaces, through reefs and crevices, to ambush prey hiding in there. It completely traded speed for maneuverability.
Then you had the ones that went the other way, down to the bottom.
Yeah.
Like Genassa.
Genassa, yeah. A perfect example of a benthic specialist. It flattened its body out, looking almost exactly like a modern ray or skate, but doing it 300 million years ago. And it had these huge, smooth tooth plates.
For crushing things.
Exactly. Specialized biological crushers. It spent its life sifting through mud, cracking open hard-shelled animals like brachiopods and crustaceans.
And my absolute favorite example of just pure evolutionary experimentation has to be in Apteryx.
The quote-unquote flying fish.
Yes. It looks like a cross between a shark and a flying fish. It has these enormous pectoral fins set really high on its body.
And the thinking there is that it probably used those fins not for gliding, but for these rapid vertical bursts of movement through the water to chase down fast-moving prey. It's just proof that they were exploring every single dimension of aquatic life.
Okay, but we can't talk about this period without mentioning the absolute poster child for weirdness, the Stythacanthids.
The anvilheads, yes. The males specifically grew this incredibly bizarre flattened structure on top of their head. It's often described as an ironing board or an anvil.
And the anvil itself was covered in teeth.
Well, tooth-like structures called denticles, hundreds of them, the whole structure was covered.
So what's the thinking there? I mean, what was it for? Was it a weapon?
That's the big puzzle. You have these denticles on the head and even on their first dorsal fin. The leading idea is that it was all for display.
Like a peacock's tail.
Exactly like that. Maybe to ward off rivals or to signal fitness to a mate. Some have even suggested it was used to physically hold on to the female during mating. Whatever it was a profound statement. It was a trait that screamed, I am different. I am specialized.
And while a lot of these weird forms were, relatively small specialists, they still had their giants.
Oh, absolutely. Let's not forget the apex predators. A shark called Cyvidus, which we found in places like Mammoth Cave, was a true monster. It could reach 8 meters in length.
So easily rivaling a modern great white.
Easily. And this whole conquest wasn't just limited to saltwater. They took over freshwater habitats, too. Groups like Xenacanthus, its name means alien spine because of this long spine sticking out of the back of its head. They established huge, diverse populations in rivers and lakes.
And were they just as specialized?
Just as specialized. Some were skinny fish eaters, others had crushing teeth for invertebrates, and there's even evidence that some of them were experimenting with filter feeding. They claimed every single niche, salt or fresh.
Okay, so they had this incredible range of body forms, the eels, the anvils, the rays. But wait, didn't the placoderms before them also have a lot of variety? Why was the shark's way of specializing so much more successful this time around?
That's a great question. And the difference, I think, comes down to the tools of their success. It brings us back to their teeth. The number one driver that allowed them to diversify so fast was their ability to develop this huge variety of specialized teeth. It was the ultimate evolutionary toolkit.
Can you break that down for us? We keep talking about dentine and this hypermineralized tissue. What made it so revolutionary? Was it like a biological ceramic?
In a way, yes, dentine is already incredibly tough, much harder than bone. But when you hypermineralize it, it becomes even more resistant to wear and tear, to fractures. This gave them a dietary edge that the slow-evolving, heavily armored placoderms just didn't have.
So let's talk about those strategies. How can we group them?
We can pretty much organize them into 3 main groups. First, you have the crushers. This is the lineage that includes the ancestors of that ratfish we started with.
Right.
They developed these fused, super robust tooth plates made of that hypermineralized dentine. This allowed them to totally pivot away from soft prey and just feast on hard-shelled animals. They basically created a whole new food source for themselves.
Okay, so that's number one. What's two?
Number two would be the graspers and puncturers. This is your classic cladodont tooth design. You have a big central cusp with smaller ones on either side. It's like having a grappling hook in your mouth.
For slippery prey.
Exactly. That multi-pronged shape was perfect for grabbing and puncturing things like fish and squid, which were also thriving in the Carboniferous. And what's amazing is that even in a single shark's jaw, the shape of the cusps could change from front to back. It gave them this incredibly versatile way of processing food.
And that brings us to the grand finale, the most bizarre one of all. The saws and whorls.
This is where things get really weird. This is where teeth were arranged in these continuously growing spirals, and they fused together to make a huge cutting surface.
And the famous example is Helicoprion.
The whorl-toothed shark. Absolutely. Its lower jaw was basically an enormous rotating buzzsaw. We're still debating exactly how it was positioned and used, but there's no question it was a highly specialized tool for shearing through something. Maybe schools of fish, maybe soft-bodied cephalopods.
So when you add it all up to the range of body types plus this incredible spectrum of specialized teeth, it's pretty clear why they took over. They had a physical and a dental solution for every possible problem.
They did.
But, as we know, that kind of perfection often comes with a price. We have to talk about the decline. As the Carboniferous ended and the Permian began, about 299 million years ago, the Earth itself was changing.
It was changing in a huge way. The formation of the supercontinent Pangaea was a monumental event. It completely altered global geography, changed ocean currents, and dramatically shifted coastlines and sea levels. The world was becoming a much harsher, less stable place.
And we can see that in the fossil record.
Oh, clearly. By the middle Permian, shark diversity is already falling off a cliff. There's a big spike in extinctions and far fewer new species appearing. The exact cause is still debated. Could be massive volcanism, could be those ocean anoxic zones again, climate shifts. It was probably a mix of things.
But whatever that slow decline was, the climax was the ultimate ecological shock. The end Permian mass extinction 252 million years ago. The Great Dying.
Truly cataclysmic. You had these massive volcanic eruptions in Siberia that triggered runaway global warming, extreme ocean acidification. It wiped out something like 80% or more of all marine species. It was the closest life on Earth has ever come to being completely extinguished.
And this is where that evolutionary trade-off comes back to bite them.
It becomes absolutely fatal. The very specialization that fueled their golden age now punished them. Remember, their ancestors survived the Devonian extinction by being flexible generalists. But these Carboniferous sharks, the anvils, the eels, the perfect shell crushers, they had traded away that flexibility.
They were too optimized for a world that no longer existed.
Exactly. They were perfectly adapted for stable, warm, shallow seas. And when the chemistry of the oceans changed that fast, when the oxygen vanished and the temperature soared, those perfect biological solutions became liabilities. They had, in a way, gotten too weird for their own good, and that spectacular diversity was almost entirely erased in a geological blink of an eye.
It's a brutal lesson. Perfection equals vulnerability when the world changes. So the survivors, they were the ones who were less weird.
They're the ones who pulled from the ancient playbook, the less specialized, more resilient groups. They managed to weather the Great Dying, proving that being adaptable is often a much better long-term strategy than being perfectly adapted.
And that brings us right back to where we started.
Full circle to the chimera, the ratfish, gliding along the seafloor today. It's a direct descendant of those less weird survivors, specifically that lineage of crushers. It's a living testament to the fact that while the explosion of weirdness was incredible, the survivors, the ones that gave rise to all modern sharks, rays, and skates, were the ones who were resilient enough to make it through.
So what does this all mean for you? I think the key takeaway here is that big crises can open up this huge space for radical evolutionary experiments. But there is always this profound trade-off between being perfectly adapted and just being adaptable. So considering that modern sharks are way less physically varied than their Carboniferous ancestors, we don't see anvils and flying fins today, it makes you wonder, what modern crisis might unlock a new era of evolutionary weirdness in the oceans? And maybe more importantly, in our rapidly changing world today, what seemingly perfect adaptation might actually be the riskiest bet of all. Something to chew on.